project, we have learned how to perform linear regression to analyze a set of data points and understand the relationship among variables. First, we saw that the line that best fits the data can be defined as the one that minimizes the sum of square residuals, and that the coefficient of these lines can be found through suitable computations. We then saw how to implement these calculations in Python and in MATLAB. To do so efficiently, we first pre-computed the terms that appear multiple times in the formulas. And we use vectorized operations, which allows us to operate directly on arrays, avoiding explicit loops. While the logic is essentially the same in the two languages, a key syntactic difference is that in MATLAB we need to use a dot before operation like multiplication and power to indicate element-wise operation. In Python, with NumPy, on the other hand, element-wise behavior is the default when we work with arrays. Finally, for computing these summations, in Python we use the sum function from the NumPy module, while in MATLAB we use the built-in sum function. We then implemented a function that takes as input two arrays containing the x and the y coordinates of the points and computes the coefficients m and q of the regression lines. And to define the function, the syntax differs slightly between Python and MATLAB. In Python, we use the keyword def to start a function and return results using the return statement. In MATLAB, on the other hand, functions are introduced with the keyword function, and the output variables are listed directly in the header of the function. We then use the function on a dataset of forest fires recorded in Algeria. And we obtain a regression line linking temperature to fire risk. This allowed us to gain quantitative insight into how an increase in temperature raises the likelihood of fires. Similarly, we saw how higher humidity can mitigate this risk, reducing the overall fire danger. As an exercise, you can try to compute the regression line for the build-up index, which is the last quantity in the dataset that we did not use. Now, a key question that we didn't address is the following. How well is the regression line fitting the data? Or, in other words, how effective is the regression in explaining the relationship between x and y? It is clear that the data on the left are better fitted by a line compared to the data on the right, but how can we quantify this intuition? One commonly used metric for this purpose is the so-called coefficient of determination, or simply r squared, which is defined as 1 minus e divided by e bar, where e is the sum of square residuals that we previously defined, while e bar is the sum of the squares of the distances of data points from the mean of y, denoted as y bar. R squared is a value between 0 and 1, and it measures the fraction of the variability of the data that can be explained by the model. If R squared is close to 0, it indicates a poor fit of the data. And in the worst-case scenario, a baseline model that always predicts the average will have R squared equal to 0. Conversely, if R squared is close to 1, it indicates a good fit. In the best case, if the predicted values match exactly the observed values, we have e equal to 0 and R squared exactly equal to 1. Try yourself to implement a function that computes the coefficient of determination and evaluate which one among temperature, humidity, and build-up index has the regression line with the best fit.